Yeah, hi everybody. Welcome to this talk about real-time tracking. Let me quickly introduce myself. My name is Felix. I'm one of the founders of Backend, a Hamburg company specialized in web performance. I studied computer science here in Hamburg, did my PhD on a couple of caching topics. And yeah, my favorite topics are web performance and data analytics, data in general, and also generating images with DALL-E. Let's have a quick look at what I'm going to cover today. So the goal is to talk about how we can track a lot of different users in real time. And for that, I first want to cover how we actually collect that data and why we collect it. Then I want to quickly discuss what that data is and what it tells you. Then going over to the analytics part of it. So how does the stack look like and how did we build the whole thing? And lastly, a bit about the results and what you can learn from that. So in order to understand what kind of data we're looking at, let me quickly start with our whole idea here of accelerating e-commerce websites and kind of collecting data from that. And you probably heard all the stories a million times. I mean, there's Amazon and other companies that have published extensive data on how good performance is for your business results in e-commerce. And essentially, it all boils down that being faster makes more money. And this is essentially what we want to track, how performance data tells you something about that relationship. And to give you a bit more context, the setting we are in here is you have your typical website, you have your user coming kind of over the network from their browser, you have to request a page, you have to do a lot of processing in your backend, your shop system to generate a response, return that to the browser, potentially load a couple of dependencies, third parties, and so on, and then still do a lot of rendering to get the whole thing shown to the user. Now, as you can imagine, there's a lot of areas here where you can lose performance, and this is exactly what we want to kind of measure and improve. So in order to do that, what kind of the whole architecture looks like is that we have a service worker, so kind of a client-side JavaScript that lives inside the browser, and each time you do a request, essentially you pass that request through the service worker like a client-side proxy, and you decide from where to load the data through that mechanism. And the reason for that is that we want to ship kind of the whole part that makes the website slow from there, and basically everything that's personalized, ship it directly from the backend. And the major part here is that during the whole process and the whole kind of loading here that happens, we want to measure exactly what goes on, if the performance is good, what kind of errors there might be seen. And kind of the main thing we do in order to get the whole thing rendered in the client is that we actually serve two different versions of the page. We serve one from SpeedKit directly, that is more or less a cached copy of the whole HTML. And we enrich that with dynamic data fetched from the original system. So we essentially have, instead of one request in the beginning, we have two. And both of them are kind of performance critical, but the first one even more, because that one is more or less responsible for painting the whole page, kind of giving your largest contentful pane and all the relevant performance timers. And kind of the whole magic that happens besides that is kind of keeping caches up to date, making sure that when someone deploys or updates content, then we want to see that data in real time. Now, in this setting, we want to collect lots of data. And the idea behind that is that in kind of traditional performance optimization, you always face the issue that when you do an optimization, you only have the before and the after. You deploy, you look, is my performance any better? But you hardly can ever tell, is it really due to my changes, or is it because I have launched a different marketing campaign and now it's winter and suddenly things change? So what we want to bring in here is basically that what you know very well from application development and kind of marketing, that you want to A/B test the impact. And in order to do that, we need kind of data to prove what happens with data and science, essentially. Now, in order to make that happen for many, many users, we had to build a stack that is more or less capable at this time to handle about 1 billion page views every month in real time. And I want to share in this talk how we built that and kind of the lessons learned from that journey. So to illustrate the basic idea, what we have is essentially the browser that gives all kinds of performance data. I mean, you have your regular timing APIs, like the navigation timings and the resource timings. You have things that come from the service worker itself. You have things like application errors and so on. All of that are essentially packaged into tracking beacons sent to a cloud backend, and then we have different timers essentially telling us something about the state of the performance. Now, what we want to do is to collect that data in a scalable fashion and basically evaluate it. So we get all the tracking data from the different browsers. We collect it kind of in an ingestion process. In our case, that consists of different systems like MongoDB, S3, and Kinesis, but more about that in a second. Then we have our analytics layer, so all the processing, all the queries that go on. This one we do mostly in Kinesis data analytics. And then we have, after that, several kind of applications pulling data from that, so things like performance dashboards, alerts, custom SQL analysis, and so on. Now, it might look easy, but it took us a couple of years to figure the whole thing out on a technical level. And the reason for that is that, for once, the data is kind of complex, so let's drill a bit into that, because it starts with the question of when do you actually send those data beacons. If you look at the loading process of a website and the kind of typical performance timers, you have a few metrics that you know right away. For example, you know what kind of previous page there was if you trigger something upon an unload event of a page. Or you have static information like user agents that more or less never change, and you have them right at the start. Then you have the download of your initial HTML, which is arguably the most important part. So you have to pull that data in order to do anything else. So you have to wait a little bit before you can see that one. After the navigation, there's all kinds of things that can happen after that, because many performance metrics rely on user input, for example, scrolling and doing things. And for that, you have to wait. So essentially, you do not have one single point in time where you can collect the data all at once, but you have to assemble it over multiple time steps. And this is essentially what we do. We have the first beacon being sent for static information, like the URL, the user agent, the session ID, things that we know kind of right after the navigation. Then we have one timer for all the initial performance timings, like time to first byte, first contentful panes, the ones that happen early and without any user input. And then we have any amount of other events, like for JavaScript errors or things that depend on user interaction, like a first input delay and so on. Now, in order to kind of build a schema around this idea of tracking performance data over the loading process of the browser, we have to first look at page impressions. So we have the navigation, we have the load beacon, and the event beacons. This is kind of the three types of beacons that we have. And all of those together form the page impression. And then when you kind of hit the next link, you click and navigate, then that kind of constitutes the second page impression. So the first question we had to answer is, how do we map the beacons to PIs? For example, how long do we actually wait for the whole data to be collected from the user events? 5 minutes, or wait for the next PI or something like that. So that's the first question we had to answer in order not to lose anything during that page impression. The second question we faced early on is, if we collect those kind of opaque user agent strings from the browser, how can we resolve those, so make them readable, extract the version numbers and operating system and so on. And for that, you usually need some context or database to look it up. Then, kind of the higher aggregation level of page impressions is sessions. So when you basically have a user clicking across various different pages, those together will form a session, and you group these page impressions together. And session data is kind of very important, because some metrics only make sense on a session level, like, for example, a conversion rate or a bounce rate. And for that, kind of the default that more or less everyone uses is to wait 30 minutes, and if nothing happens in those 30 minutes, then you consider the whole session to be finished. Now, this kind of sounds easy. So we have page impressions, we have sessions, all of those collected from the individual beacons. So where's the actual challenge when processing and collecting all that data. To understand that, here's a kind of rough overview of what we want to do. We have basically the schema where you have user agents joined with page impressions, and each page impression basically has any number of beacons, and any number of page impressions make up a session. So that's our schema. Now, where we want to get is that we can do more or less any query over time and ask any questions about the data, like how was my conversion rate yesterday? So to get to that point, our first approach that we tried is to do daily aggregates. And this is how that worked. We basically had all the different data coming in. So on the one side, we had data that we, on request level, collect through our CDN Fastly. Then we have data that we collect kind of through the browser, the performance data. For that, we had a kind of buffering going on in MongoDB, where we first wrote all the beacons, and then in a periodic job, we pushed it into S3. From there, it went on to our data warehouse, Amazon Athena, so kind of a hosted Presto. And after that, basically, we had a BI dashboarding layer that pulled data from QuickSight and kind of fetched it from Athena, which looks more or less like a reasonable architecture, but there's a couple of issues here. So the first one is that since we have so many joins, like different beacons and sessions all kind of making up a complex schema, is that those queries were extremely slow. Then the other issue was, since we only did the kind of periodic writes, and I think 60 minutes was the default to write those data back, and then there's additional time to execute the query from QuickSight, we had 90 minutes of kind of discovery time before we could see any change. So that is hardly real time. And then basically, because on top of that, we did not do the queries in real time, but we kind of pre-materialized them overnight. We basically had to wait. If we made a change on Monday, we had to wait till Tuesday to observe and analyze that change. And on top of that, there's actually kind of two different use cases here. The one is we want to have more or less real-time simple data for alerting. Let's say things like we observe a certain kind of high threshold of JavaScript errors. It's more or less a very, very simple alert that we want to fire. But we also have complex analyses like how is the correlation between my histogram of largest contentful paint to conversion rate, and that one over time is very, very complex. So there's a big gap between those kind of easy to do analyses and the more complex one, and the processing time was just getting out of hand. So we thought there must be a smarter way to do all this. And we went into a prototyping engagement with AWS, and we rebuilt the whole pipeline for better scalability, for better real-time access, essentially. So what we did was to first get rid of MongoDB in the whole thing. So we eliminated kind of one single point of failure that was also very slow. So directly writing to S3 was the key. And then after that, sorry, not directly, but through a stream processing engine, writing to S3 and getting rid of the buffering inside MongoDB. And the architecture we chose is that the stream ingestion happens in Kinesis on AWS, and on Kinesis we run Flink, and the managed service of that is KDA, and that basically writes to both S3, kind of the historic data, and into a serving storage for the whole dashboarding on top of that. So this means since we have a faster kind of stream processing ingestion, we do not have to wait those 90 minutes of discovery time. Still, we wanted to have the whole kind of batch part of things because you might want to run complex queries still. So we still kept the data warehouse that pulls from the whole data from S3 and from there basically sees the whole complete non-aggregated data. Yeah, there's also a moderately boring scientific paper if you want to learn more about this. For the processing in the stream I mentioned, we used KDA and Flink, and I'm going to show you in a second what we do in there. And for the serving storage, we opted for Elasticsearch, and the dashboarding part, we opted for Kibana. Now, the shiny new schema looks like this. We have still the same stuff at the top. We have our beacons, user agent, page impressions and sessions, but now processed in a streaming fashion instead of these materialized views that are computed kind of once every night. We now have a new format of pre-aggregating things in 1-minute aggregates, because the idea is that we still need some pre-aggregation to be very performant for the dashboarding layer, but we do want to do it in a fashion that you can still run complex queries over that data and that you get rid of the delay of waiting basically for long materialization periods. And the dashboard obviously then can be updated in real time. Now, this means we have 3 levels of aggregation, and there was a previous talk by Wolle who went a bit into kind of the tricks that we need to do in order to get that data clean. We have what we call partial page impressions that contain things like, hey, someone clicked on this page in this browser, had these and these timers, and essentially a lot of data from that comes in, then gets grouped into these windows of 1 minute. So we basically put them all together and have to perform some pre-aggregation. So as you can see here, we actually put together the data of the first contentful paint performance timer into a histogram. So from the histogram, we can later compute other things like quantiles and look at the complete distribution and so on. And the nice thing is that you can compose these histograms. So we have basically one summary for each minute, and then if you want to run a complex queries, you simply add the 1 minute aggregates together, sum up all the components inside this histogram, and then you have the complete histogram over a time frame. Yeah, and then basically about the part that happens within Flink, the thing we have to solve is, so when the data arrives from Kinesis in real time, the first thing we need to apply is the stuff that Wolle talked about earlier. We need to get rid of data that is malformed or just contains garbage timers and so on. So what we do is to validate the schema, and if something looks wrong, we kind of write back the invalid beacons for later analysis and only kind of pass on the ones that look okay. And then another kind of stateful component in that whole stream processing part is bot detection. For that, we kind of look at kind of suspicious patterns like very long sessions or those that never convert and kind of hit a lot of traffic and all come from the same IP address or from the same ASN. If those patterns occur, we kind of write back the metadata of that into DynamoDB, so later on we can re-identify suspicious ASNs, IPs, and user agents, and so on. Then we have the resolution step that I mentioned of the user agent, so kind of turning an opaque string into something that later on we can easily analyze, group by, and read. And the first part we then write back is the page impression windows in 1 minute sections, the session data also in 1 minute sections. Sorry, these are the buckets that are occurring here. These are actually 30 minutes windows that go into basically Parquet files on S3 that later on Athena can pull all the data from, and this one is the pre-aggregated. So doing the split makes a lot of sense because we have on the one hand side this data that is very fast to query for our dashboarding layer, and we have the complete data if we do kind of complex analyses that require the actual base data, not the pre-aggregated form. Yeah, that's what's going on inside our Flink cluster. So we are quite happy with that solution because it's much faster, much more scalable, and overall kind of a very much better solution than our initial MongoDB thing. So the last part I want to cover is actually what we do with that RAM data. So now that we have collected these millions of page impressions, so right now we are collecting roughly 6 billion beacons per day, per month. That is around 1 billion page impressions roughly, and around, I think, 300 million to 400 million sessions. So the idea, as I mentioned, was that we want to kind of test things for our product. So what we do is actually to have one group of users enable SpeedKit and the other one kind of load the website without executing our service worker. And the reason for that is that we can now measure in both groups what the performance looks like and other parameters and compare in a clean A/B test how that boils down into your different metrics and how users might behave differently. So to show you some examples, this is what it looks like kind of in a shiny marketing slide, but let me get to one concrete example here. This here is data from Zwilling.com, kind of a very traditional company selling knives and kitchen stuff online now very successfully. And there we did that kind of test. So we had two groups compared to each other. And this is what you can see in that histogram here. You have two curves of performance. You have one that loads with SpeedKit. This is the blue one where you shift a lot of users in their largest contentful paint in the area below 1 second. And you have the original one that has kind of higher page load times. And as we measured along with this data also business, we could confirm that this kind of improvement led to around 2% uplift in conversion rate and around 5% uplift in revenue. And this is kind of neat because we can not only kind of do the whole analysis at the end of the whole test, but we can actually perform it in real time and see the data coming in and also react if we see something is off, like errors or something not loading as fast as we would expect it. Yeah, and the other use case we have and are just getting started with right now is a real user monitoring dashboard. So since we originally did all this only for the sake of doing A/B testing, we later on realized that this data might be quite valuable kind of in itself. We are now opening it up to basically do your own custom analysis, and we chose to build the whole thing on top of Grafana. So we have kind of a default dashboard with different widgets to track your performance, like I think by default in a 7 days window to see, did my performance improve or did it get worse? You see all your typical indicators for your web vitals. And you can, what is quite nice, drill down quite a bit. So you can not only see it on a daily basis, your trends of your performance, but you can also kind of look into certain segments like your different page types, your different browsers, compare mobile to desktop, for example. So this is kind of very interesting. We're just getting started, so this here is not kind of a complete RAM solution, but we figured out that since we have the data anyway, we want to open it up, and we are seeing right now that this turns out to be quite useful. And that's already what I had. Thank you very much.